Live once again with our Wednesday hardware live stream here for Goliath. My name is Chris Gamble. I'm the head of hardware and developer relations at Goliath. I have a new setup here, so we'll see how the sound and everything goes. If you are in the chat, if things look or sound funny, aside from my normal voice, please let me know. Today we're going to be going, this is the 5th session, which I had expected we were going to be done by now, but we are not. As it goes with layout, sometimes you want to make sure, well, when you want to make sure you get it right, you go back over your own decisions. And as you've seen in sessions 1 through 4, there's been some iteration on what we're actually building and what we want to do here. So the whole thing started with, hey, I should build something with a NRF 9151. That's a board that we had the development kit for. I'm excited about the smaller size, the whatever. And then it kind of morphed into like, well, what if we made a module that could work for everything? And starting from our open source Elixir board, which is something we released a couple weeks / months ago, this is kind of a drop-in for that, and really a drop-in to the Elixir form factor. And then the idea being that you could take this module, and once you're done with the Elixir, you've used microbus click headers and clickboards to prototype, you could pull this module off, put it on something smaller, something more compact, and you're off to the races. And you're also more immune to a lot of the part shortages we saw in 21-2, 23. I'm definitely still worried about that in 24 and beyond. And even though we're in a much better place. And also, though, the idea that you could have different vendors, different capabilities, and you it's kind of a minimum set of features that you have on the castellated edges of this Dram module, which is what we're working on here today. And the minimum set of features basically should carry you through for future modules as well. So say you wanted to switch to a Cat1 modem or a Cat4 modem, Cat1 BIS. These are all different types of cellular modems, or you wanted to add different connectivity, different capabilities, different lower power stuff on your board. The idea being that because the edge of your board is acting as a effective abstraction layer. This is hardware as an abstraction layer, not hardware abstraction layer, that it would allow you to be kind of ready for future changes. So let's take a look at where we are and kind of what we've been doing in the past. There's a tiny view. How about a bigger view? Here we go. Okay, so this is the Dram project, and this is the 3D model. You may notice a large Goliath logo on here now. Oh, I meant to switch this. Did that not switch over? Interesting. Okay. Well, I had it in mils. Switching between mils and millimeters. Oh boy. This is still stuck in mils. I'm guessing I'll have to make a small change in order for it to redraw. Maybe if I do this too, switch it into the 3D mode and switch it back. There we go. Yep, that did it. So this is a 24 by 34 module. That's millimeters. And yes, some of the things that have happened off camera in the last video, in session 4, what we did is we routed the RF here, and you see these kind of squiggly traces. This is all based on the stackup. And if you don't know, the stackup is how the height of the different layers of your PCB. One thing that has changed though is the stackup characteristics are the same. That the RF is valid here. However, I added another layer because in terms of the stackup, I wanted to have controlled impedance possible on the top and bottom. And so what I did is I have a reference ground layer on layer. So top layer is layer 1, layer 2 is ground. Now we have 2 inner layers, which are going to be signal layers, and then another ground layer, and then finally a bottom layer. Probably one of those inner layers will also end up being a power layer, just because it'll make it easier here to pass power on the board using one of those layers. But 3 signal layers should be more than sufficient for routing all these signals. I did start to get a little bit nervous between the controlled impedance on top and bottom and the need to have relatively tight routing, especially for things like as we move up into Dram 2, 3, 4. Not that we couldn't do a 4-layer board on one of these and a 6-layer board or another, or 8 or 10 or whatever. But not that we couldn't do that, but this is I'm going to start with 6 and see how it goes. In terms of the actual cost differences, really, as you move into volume, especially with smaller boards like this, I already have some specialized characteristics like the castellated edges and the controlled impedance, and I'm probably going to use a fancy solder mask color, things like that, Enig plating. Nothing completely out of the normal, but out of the super cheap realm. The other thing that came of the switch over to the 6-layer board is the fact that I had previously said it was going to be a 0.8 millimeter height module, but now because of the stack up, it is a 1.2 millimeter. We can actually look at that. I actually inserted the values here. So these are pulled from the JLC process here, the 7628 6-layer process from JLC. And so that's what you see, that we are 6 layers here. You see it's actually not exactly 1.2 millimeters. They call that out and they're like, if you exactly want 1.2, you need a different one. But this is ultimately the one that I liked. It also matched in terms of the prepreg material and the heights of these things. It actually allowed me to keep a lot of the capabilities there as well. So this is the stack up that we'll be using here. Other things, so if you don't know KiCad very well, this board menu basically is kind of the control panel for your entire design. And so things like board finish, you see this is where I put castellated edges. These different layers here I added. Now that I have 6, I renamed them. So front copper, I said front ground, inner 1, inner 2, background, back copper. And one of these will probably actually be a mixed. So maybe layer 2, inner 2 will be mixed because it'll be power plus potentially some errant traces in there. But other things that I ended up pulling out of here is actually capabilities from the capabilities page of JLC. I wanted to make sure that another kind of, as you're playing with your pricing calculators and stuff like that, one thing that's really going to end up impacting your costs as well is going to be your via sizes, how your vias are plugged, if they're plugged at all, that sort of thing. If you're doing blind and buried, I'm not doing blind and buried, but I am doing some of the smaller ones. I believe, let's see what I said at that actually. I think it was 0.25 millimeter drill. So this is under net classes. And you see my default here. So, okay, so my default via hole size is 0.2 millimeters. And then the via, so that's the total size around that via hole, is 0.35. This will drive costs of basically any manufacturer. And, but I like it for, really shrinking down the vias, between 0.2, 0.25, 0.3 millimeter vias, you start to, basically once you get beyond 0.3 millimeters, you start to incur costs, but I think it's worth it for the stuff we're doing here, especially when we move into the other boards, if we wanted to keep this sort of stuff. You see I already have some controlled impedance lines. This is what we did last time with the 50 ohm net class. So, and I assigned that net class to the various lines here. And so now what we're left with is a bunch of connections. I also mapped my, what I usually do in KiCad is they reassigned some of these keys. I'm not a huge fan of how they did it, but I actually really like to have, and let's see if I can do this. Let's go here. Let's go here. And you see I have on the right side my various layers, but if I hit 1, you can kind of see in the upper layer or upper thing here as well, 1, 2, 3, 4, 5, 6. I assign those because I really like to be able to switch between layers by just hitting the number on the keyboard. I find that to be very, very useful. Not everybody does that, but and you could set up your hotkeys however you'd like to. Keyboard aficionados will talk to you about their keyboard preferences all day long. What I set though in the net classes here, you see all the default. This is just the default net class for anything that doesn't have, for instance, a 50 ohm assigned here. 5 mil space trace. And now that could be lower, specifically at JLC, that could be lower. You could go as low as 3.5 mil. I have made that mistake many times where I go to the smallest size and then I get hosed later when things are too close together, or you move to a different board manufacturer and they're like, actually, it's 4 mils instead of 3.5 mils. and to size up from, basically having your traces super close together at 3.5 mils and then sizing up to 4 mils, it is a nightmare. So it's best to start at a larger size from my perspective, and then move to something smaller as needed. I'm just going to take a quick look. I don't think anyone's in the chat. If you are, hello. Oh, we have 3 viewers. Thank you for watching, or watching after the fact. But yeah, if you do have any questions, please let me know. I'll keep this down here so that I can see the comments a little bit better. Okay. What can I do with this? Can I do anything there? No, I don't think so. Okay. Let's keep going. So one thing that has been added also since the last stream, I've assigned a couple other signals that were hooked up off camera. And this is just in the schematic. So that's here. Specifically, the ESP32C3. So basically, I have these reserved pins at the top of the Dram pinout here, and those are up here. This is one of the reasons I wanted backside castellated edges, or backside controlled impedance rather, because I wanted to be able to route 90 ohm for USB. I still have a little bit of concern going through a castellated edge with D plus D minus. I talked to Arturo, who does the 2340 stamp, the solder party, just asking about, he also passes USB signals through there. He said he doesn't have a lot of issue with that, which is great. I really appreciated his insight there. But we'll, maybe put some resistors in line there or something. But the main thing being that I assigned those to, so this is D plus D minus, those on the ESP32C3, that goes to GPIO 19 and 18. So I need to then go and create a differential pair on 90 ohms. So I might leave that one till later. I would like to start. I mean, I could just, I guess, keep a path here. So I think if even though I don't have it set up, I don't think. Yeah, it does detect. I'm just going to use this as a placeholder right now. Oopsies, got to route it around the vias that I got there. Doesn't seem to like that. There we go. And I'm just, this is on the bottom side. Those ground vias shouldn't have any impact here, but I'm just going to do this as again, just a placeholder. So, okay. Let's try this one more time. Do a little swapperoo. And then these should be better suited. There we go. So, those are not controlled impedance yet, because those are not set for 90 ohms. But those at least kind of have a pathway reserved. That's the main thing I want to get. It's just make sure I have kind of the most important stuff routed first. And because I'm going kind of a straight shot from the top of the board here straight down to the ESP32C3, I want to do that first. All right, so now I have access to other things on the pin edge, right? So now we're trying to basically kind of hook everything else up. One that I wanted to also route early was the analog signals. You see 11 and 12 are analog. So I'm going to actually route those on the inner layer, which is layer 3. Let's do that first. Oh, I'm still in the, oops. I was still in the differential pair mode there. So this one is relatively simple here because we get to just do a straight shot here. There we go. When I'm routing these, when I'm switching between layers, I'm just hitting V for via, and then it usually switches to the next logical layer, I think, because it knows it's trying to hook it up to the signal. So because it already has the DG11A signal in this case, when I hit via, it was trying to connect it to the pin that was on that layer. So there we go. Now you see those signals are kind of chopped out there. Might want some spacing in between just to get the ground core in between there. Okay, so, and that's a really nice kind of benefit from the fact that we're going, so because we're going from a castellated edge, the castellated edge kind of goes along the column of all 6 layers of the cake, right? And so because one of those layers is inner layer 3, we basically just get to connect from that castellated edge to layer 3, and away we go. This is also helpful for kind of leaving stuff off the top layer, not necessarily something we need to do, but yeah, we really kind of benefit from kind of using the across version at this point. So we can just keep routing here. So what this is kind of shaping up in my mind to be is that red, the top layer, layer 1 f.cu, is kind of showing me, it's vertical-ish. And usually in those cases, I would, kind of maintain like one goes east-west, the other one goes north-south, right? Especially if I'm on a 4-layer board, that really starts to help to break those sort of things out. I could also potentially, because on layer 6, we are routing vertical, right? Because of the USB here. Potentially we should have layer 6, the backside ground, be our north-south, and then our top be east-west. Let's take a look here. Yeah, I am kind of liking that actually. So let's go back, and easy way to do that would just be to delete this. And so this will just give us an extra hop here. We'll still have to connect to the top side here. But as long as you're close enough to the actual part, then no problem with it. That little jump is no problem there. Let's try this on layer 3. And this will be to layer 6, to layer 1. Do not want to do via in pad like that. So hit B to redraw our zones. And we can get rid of this. There we go. All right. On the back side here, now another thing to note, I guess if I go to the, I had put these programming points on here, and I did that for the ESP32C3, thinking about, so these are signals that are not going to be accessible on the castellated edge. However, for things like programming the ESP32C3 with the ESP-AT firmware, probably want to do that at the factory. You might, in theory, I've seen on some modules where they actually make these signals accessible. In theory, you could basically float the module and have kind of a solder blob underneath here. Definitely not the purpose of this, but at least from a programming perspective, that is something that that I'm very interested in, having kind of a standard pinout, so you could go and access the ESP32C3 without having to have its own SWD header like we do for the other one, right? So really only expect the programming header to be required for the primary module, in this case the 9151. In this case it would be the the NRF52840. So basically having kind of secondary programming capabilities, so you can go and access this easily. I'm not too worried about Dram 234 yet. The only key thing being, if I see any needs for changing the castellated edge pinouts, that's really going to be the big one, right? So if you have any needs where you're going to be like, oh, I definitely need to change the pinout, you do that as soon as possible. I don't plan to do that, but yeah, you just never know. This signal is making me a little nervous here. Let's put this one on layer 3 and route this across. And I'm basically going around, and this is kind of a low and slow signal, but I'm not a huge fan of doing this. So the reason I'm okay with it being low and slow is because it's going, it's going around the RF basically. Maybe even up here, and then have this go on layer 6 down. Yeah. And then let's go across. I might change that to layer 3. Interesting that this is on 2 different pins here. Let's take a look at the schematic real quick. It's pin 9. 9 and 10. Okay, so there's an reset, an inverted reset, and a enable pin. I think I got to double check on this one. I think on other designs, this is actually a pull up to 3v3. So I just need to make sure that that is correct. We'll hook it up for now, but put a note here. Okay. I think on the Elixir it may have been. Okay, so something we haven't talked about yet is the incoming power. I would like to, we talked about inner 2 here. And so what I'll do with this, this is the power plane, that's the ground plane rather, that's going through all of these. I'm going to copy it. I was going to Control D, and I placed it there. Now we have 2 of those. I'm going to turn off all these ground layers. We're going to switch the net as well. We'll put it on layer 2, AV3. Dram 1, 3v3. So the reason we see multiple versions here is because these are different sheets that we have in the schematic, and we're on Dram 1, so we're going to select Dram 1. All right, so now we should see a fill here. And what you can come out, it's not super easy to see. Let's look at only this layer. Let's see, show, hide all layers but active. Yeah, there we go. Okay, so what we see here is you see how there's a kind of a scalloped cutout around all these pins, but on the incoming 3v3, this is connected here. And so that's pretty nice. Show all copper layers. All right, so turn that back on. We also do have incoming incoming decoupling. So that's here. And if we look at it on the schematic, that's the incoming on the to the module, right? So this is the 3v3 from module. So pins 5 and 6, as we're looking at here, and then we have 4.7 microfarad and a 0.1 microfarad. So these are both on the top side. We should be able to just route these with. Do I have any fat traces? I don't. Okay. So I'm going to set up a fat trace. I don't know if people call them that, but you see these are predefined sizes. So this is basically, if you're using the W key, you can switch from your default sizes up to your to different sizes you might want to have, right? They're basically like non-default sizes. What you see that I put in here is actually, this is a 3.5 millimeter trace. It's actually 0.089, but I was round up because sometimes 0.089, when you send it to JLC, they're like, no, that's actually a DRC violation. So I always round up a little bit, but that is the smallest you can get. And so that's one of the track widths. I'd said, by default, you want to have, a larger size than the minimum. But when you do want the minimum, it's really nice to be able to switch to it with W or Control W, kind of cycle between these different ones here. So let's pick a fat one. We'll just add a 1 millimeter trace, and let's see how that goes. So if I hit X to start, I get real fat now. Ooh, yeah, look at that. Some would say that's too much, much too much. Okay. So this one, the top side layer, that is, so that one's, if you look at the setting I have for the ground plane, so these are I have ground planes on top side copper, and ground copper 1, ground copper 2, and backside. So those are just always there. But you see I have these set as solid pad connections. And so that's why you don't see any cutout there. If I switch this to thermal relief and hit B, you'll see a cutout happen around here. I really prefer to have solid, especially with these small format things here. So we're going to switch that back to solid. It is tough for soldering, but if you're doing reflow, it should be fine. It's even an argument for, if you're doing a module like this, where you're going to be doing reflow on the module itself first, and then potentially reflowing the module later. This could actually help to have more thermal mass, so that the castellated edges will kind of melt solder first, and then all the stuff on the board itself will stay put. That's my theory, and I'm sticking to it. Okay, let's take a look here. X to reset everything. If you don't remember from past streams, you would see that I've got a lot of stuff going on here, but Dram 1 is the one we really care about. And we're making some progress here, which is great. Let's move this over. Also of note, I did a bad thing here where I did not go and make a new module. All I did is I took the NRF 9161, which is a little bit longer, and then I modified it and just squished it down. That's why you see any of the text is 9161, and it also looks squished. So that's my cheapo hack to not have to go and build new 3D models. But you see, it actually does fit pretty well. And it's really just for show at this case, in this point. So, all right, so we've got our incoming. We have one of our incoming capacitors hooked up. Let's do the same over here. Switch back to this layout. There we go. We've got some incoming decoupling caps. We also have some caps for this is for the module itself. This is for the NRF 9151. So these are all sets of 47 microfarad, massive beastie. That's not going to work. So you got to switch that down. So we're going to switch to the 0.2 millimeter track there. And these were borrowed from the Elixir, so I have to double check. I do have access to the DK, but that's under, those files are under NDA, so I can't share them here. But I will just double check to make sure I'm not missing, usually when you're starting with a new design like this, it's best to just copy the vendor stuff as much as you can. All right, how are we doing here? So let's switch back to the net class width. There we go. So this one is nice and easy. You could do this, or we could even just switch to layer 3. And already, I mean, you're just seeing how much easier it gets when you have a 6-layer board here. right, so we've got let's do that. And then we're going to do this. And this is the okay. You said this is the secure element. This is the ATEX 608, which I'm not sure if I discussed on previous versions, previous sessions here. But the reason we have a secure element outside of something, that so Nordic has a secure partition in the NRF 9151, we could still use it. The reason I am not necessarily planning to do that is that I would love to have it be standard actually across. So if we used the external one on the 9151, then we could also translate that to the NRF 52840. Basically, any part that doesn't have secure storage, we can still use. We could still use this stuff. All right, look at that. So you can just drop a via there. So if you're not super, if you haven't done a lot of layout, in this case, because on layer 4, we just have this solid ground plane of power here, which is the 3v3, we get to just connect that up. One thing that this does make me a little bit nervous about is the fact that we don't have any way. So like say we had a short on board, there's no way to really test it because we're hooking it up directly to the castellated edge pin. I guess we could bring it to, we could say, bring that stuff in first, put it through a 0 ohm resistor, and then dump it into the ground or the power plane. And I'm not so sure about that. But let's keep moving. That might be one where I go back and watch the tape later, and I'm very upset about it. All right, so once again, just highlighting how easy this has gotten with the 6-layer board. Almost too easy. Finally, small challenge. So we take this all the way across and go to layer 6. Okay. Same thing here. It's vertical-ish, right? Where's this one going? Another thing we could be doing here that I have chosen not to do, or I may have done off camera a little bit, is refactoring where some of these pins are on the module. We do have a lot of flexibility, especially at this point in our design, that we do not, these are the G of GPIO is general, right? And we can actually switch this around. These are all configurable in the board files for Zephyr. So we still could switch these around if we needed to. I had already oriented, so I chose the orientation of the module of the 9151 SIP and the ESP32 really around the RF. And I think that is the best method that I know. But in theory, you could, rotate so that your pins are a little bit in a different location. You could reassign pins on the edge of the SIP and then just change the board file. That's another possibility here. So, all right, let's do this one. This is the coexistence pin. So we're going to do this, go to layer 6. It should be okay to go underneath here. Remember, this is separated by 1.2 millimeters worth of stuff here because we're going top to bottom. And this, the GPS coexistence pin is both tied to the GPS and is a low speed signal. So I'm not too worried about that. In theory, we could go out and around, but I think we'll be okay. I don't expect us to have any problems there. This is a 3.3, so we should be able to actually bump this up. You can kind of see, actually I could change some of the opacity here. If I change the opacity, all these different layers, I think there's a faster way to do this, but I'm not 100% sure what it is. Color. I'm just hitting the middle mouse button. All right, that one's already good. Red. Just taking it down to like 80-ish. And you can start to then see some more of the other layers there. Kind of see through the layout. So, and really just seeing that there's anything there is kind of useful. Excuse me, sorry. That via is not playing nice. I just want to drop a via to the power layer. And basically now you see that it's connected on layer 4, which is inner 2. That's the 3v3. And it's controlled by this GPS enable. Okay, so this one is going to the ESP32C3. And let's take a look at this part here. I'm going to change this over here, turn off the layer window. That is a pull-up. Okay, so these are the strapping pins for the ESP32C3 at boot. They're IO2, 8, and 9. Need to be pulled up for different boot modes. Specifically, we want to be starting generally out of Flash, I believe. There is, let's see. Yeah, so if we search for GPIO 8, there is a strapping table here somewhere. There we go. Yeah. The default configuration is weak pull up. And so basically though, we want to have these all pulled up by default, and then we can, when we want to have different boot modes, we can do that. Also, the one of the pins that allows you to move into that programming mode is available on the bottom side. So when we're programming it using those bottom pins, we can do that. All right, so let's go to the top side here, layer 1. Just get these in line here. I'm not actually sure. Let's pull up the schematic here. So this one is going to GPIO 9. I'm not sure why this isn't showing as going there. Oh, there we go. Yeah, it's weird. When you see those, that kind of red highlight there, that's interference based on the courtyards of the part, and shouldn't actually do that with the traces unless you're directly over a trace there. A little bit easier to see if I do Control-Shift-B. You can see I turned off the ground pores there. I think I have a layer. I must have a layer turned off here as well. Yeah, there we go. So there's the actual courtyards, and when it comes to that's going to give a DRC error there. There you go. There's the green. Gonna hem myself in there. Anyways, when I get to, if I had these overlapping one another, then when I get to DRC and do the actual error checking, it's going to complain at me and say, hey, these parts are too close together based on your courtyards. Courtyards basically are saying how close things can be to one another. Another thing we could do, and I have broken the barrier of switching to 0201 components, specifically for the RF stuff. So we have 0201 based on size there. I may end up switching that back, but as of right now, we do have 0201 on board, so important to know. I think these are 0402. And it always kind of starts, when I start layouts like this, I always kind of think I kind of have a worst case scenario in my head and I plan for that. And then later I'm like, oh, that wasn't that bad. And we are definitely hitting that sort of thing here. So this is the pull down for the antenna coexistence. This should actually probably be, let's undo that. Let's move this guy up here. I think we'll have space. Yeah. Again, if you're new to layout and you've not seen this kind of stuff before, it can be confusing with all the different kind of stack of colors on top of one another, stack of colors, stack of things that are here. One thing I highly recommend as you're learning layout, as you're doing this sort of thing, is kind of keeping your 3D model or your 3D version up on top. I'm only working on one screen because of the constraints of a live stream, but having this here can really help to visualize and say like, oh, actually that one part is actually on the bottom side, even though it's blue versus red. So, they really rely a lot on colors, which can be very confusing for, your brain as you're putting this kind of stuff together. So, yeah. And here's those 0201 parts that I mentioned. That was really around the size of the pad as well. I think that really matches even though it's a smaller part, the pad size really fits the closer you are to the trace width, the better off you will be in terms of reducing nonlinearities. Okay. Discontinuities, that was the word I was looking for. No one's here to correct me. All right, so I think we're still doing okay, space-wise and everything. I'm going to, let's route this one now. What is this one? This is the C8, yeah, this is the TX. So this is coming from the 9151 in this case is the boss, right? It's running all the code. We're programming it over SWD. It's talking over cellular and GPS in Dram 1, in this version of the Dram. But it needs to talk to the secondary modem, in this case, the ESP32C3 running in ESP-AT mode, so that it can do things like Wi-Fi locationing and things like if we ever play around with the Bluetooth side of things, you can actually use the AT commands to control Bluetooth as well. So you could talk to Bluetooth devices nearby. You could basically kind of offload a bunch of Bluetooth capabilities there. Similarly, if we wanted to have, like on the NRF9160DK, they have a secondary Bluetooth modem on board for multiple reasons. One for USB, the other for kind of making it a gateway. We just actually published about Bluetooth to cellular gateway using beacons. And you can actually set up that NRF52840 as a secondary processor, basically HCI LP UART, I believe it's called. So basically it's like a Bluetooth modem. And so if we wanted to make a little cellular to Bluetooth gateway on the Dram form factor, we could do that. We could do that both with ESP32C3, or we could do it with, I guess that would be Dram 5, where the NRF9151 is, again, the boss, that's the primary. And then the secondary in that case would be the 52840 or equivalent from Nordic. And then you just program the 52840 as an LP, HCI LP UART, and then you have a little gateway just in the same form factor, which is pretty darn cool. Okie dokie. Giving away all my secrets. Live. Ain't no taking these back. All right, I'm going to stop talking. So one thing I'm noticing here is I do not have... so what I expect the behavior to be happening here is actually the bump. And I'm going to... So I right click as I'm running trace. And right now we're on walk around. I love shove, though, because when you start doing this, now look at that. I just hit V, and it's like, oh, I'll just move all these traces for you, sir. No problem. So I didn't realize that wasn't the default. That's why some of my stuff isn't moving. Now, when you need to be careful with shove, though, is look at that. I just had these controlled impedance traces that are, well, the kind of the runway for these controlled impedance traces, because these are not yet set up as controlled impedance traces. So one thing you can do is go here, hit U. Oops, let's highlight both of these and hit U a couple times. That highlights the entire net. And then what you can do is right click, and then you can turn on, you can lock these traces. And that's really nice actually for when you do have shove turned on, right? So now I can go back to here, start shoving. So I could shove other traces around, but it will not shove lock traces. And so that is a very good idea if you're going to start using shove. When push comes to shove, God, terrible. Nobody's here to stop me making puns. If you're watching after the fact, you should have been here. Talking to you, Dan Mangum. Dan said he was going to, Dan, who's been very kind and been at many previous layout sessions here and listened to me ramble for God knows how many hours. He said he was going to make a game time decision today, and it seems that the game time decision was, well, our head of engineering is taking care of all the important stuff at Goliath. So that's great. All right, let's keep this train a-rolling. So now we have basically all these are going to be running all the way down to the bottom here. They look like they fan out pretty well. So let's see. We're going to have to go around the controlled impedance traces there, but that shouldn't be too big a deal. Let's do this. Oh, no, that's not what I wanted. I wanted to stay on layer 6. Let's do that. We can just shove these out of the way, which is nice. We are now once again into the RF territory there. So let's just make sure we're, well, that is literally right underneath the trace. Excuse me 1 second, just going to take a quick nose blowing break. I should have some kind of hold music for that sort of thing. All right, so this one doesn't look great. So we're now into the lower 2.4 gigahertz realm. Am I still routing? Layer 1, there we go. So this is the 2.4 gigahertz coming off of the ESP32C3 or other, other versions of the board. Then there might be other chips. But one thing that is happening here is we have the in the lower left corner for future versions of the Dram, so Dram 3, which is using the ESP32C3 as the primary, and then the BG77 as the secondary cellular modem. Because the ESP32C3 doesn't have a lot of GPIO, as you can see, there's not a ton of pins here. We are going to use a GPIO expander, but those are all in the lower left corner of this design here. And so that's why all these signals you see here are DG, XX, S, and S being simple for basically just on off, no fanciness like PWM, no analog, nothing like that, no SPI. So basically any signal on that's connecting to a DRAM module should be just kind of high-low. And for a lot of designs, LEDs, things like that, like honestly, it's a lot of what I use, but we still need to hook them up. So let's see what else we have available to us. Okay, so this one is going there. In terms of like the layout, it actually, these look pretty good. Just wondering how I can route these in a cogent way. So I think one thing I could do is I could just bump these over. And then this one, what is this one? Let's bump this one over too. Recall that I only really need to maintain the controlled impedance trace here. So I think. So I think what I'm going to do is have like a little high. Oh, yuck! Sorry, make this bigger here. So I think I'm going to have a little highway of orange signals kind of going up and to the right, or up and to the left here. So let's just try that first, and then they'll go vertical on the blue layer, and then they'll connect to the red layer. If we need to, we could always bump this chip up. This is the HSM chip. Bump that up, but we do have a decent amount of space right here. All right, so let's first delete this trace U. And that's on layer 3. We're just going to kind of get up and pass the RF there. And is this the last one? Let's see, I think that is. Yeah, that's the last one. Now, generally, layer 3 is meant to be a, I don't know what's happening here. There we go. Generally, layer 3 is meant as a kind of east-west. So I am breaking my own rules here, but I think we should be okay. I'm not sure why it keeps doing that. All right, so now let's go to layer 6 rather. Let's redraw. I think I'm gonna have to move this one. Yike. All right, so we'll move that there for now. We haven't hooked up any of these pads yet, these test pads, which are the ones I mentioned for programming the ESP32C3, but really kind of feels secondary in nature. I am also going to, there's really no reason to have these so far out here other than to make the bend, but let's go and unlock this track. So we go to locking, unlock. Let's go and see if we can drag these over. Whew, didn't like that. It's ad hoc, but we'll make it work. Okay. So these are, again, these are not currently controlled impedance, right? We just want to have kind of the lane set up. So it seems like this lane is relatively sufficient for what we need to be doing. Let's select this again, select the whole thing, go to lock. And that then should give us enough space to route from layer 3 on up. This is now on layer 6. Go north. Oh, that one's a bit of an oddball actually. 3. There we go. Okay. So the blue layer still has grounds on either side of the controlled impedance trace there. DGL5S is one where I could see us switching that later. Okay. Now this is closer to what I expect. Yeah, yikes. The downside to push and shove. But we can refactor these later. Looks like the lane is open, so that's good. And one more. 6. Oh, whoa, 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 whoa. Ah. Yeah, see the inner layer there got shoved around a little bit. It's okay. There we go. Oh, these are those analog signals I was worried about. So actually, let's go and lock those too. We can always unlock later. All right. So now we're on to a couple signals here. Let's go on layer 3. Layer 6. And again, we really benefit on castellated edges because you don't have to make that last hop up to top layer, because castellated edges is all layers. So this is that one I moved for the controlled impedance lane. I think I still want to move it again. Yeah, this one's a little tricky. That one's locked. Three. Six. All right, so this one is this is something that still might change. One thing that you see here, this, go to layer 1. This memory footprint is actually much smaller than this one. This is the memory. This is the memory size. I think it's a SOIC 8. Whatever the heck that size is. Maybe it's smaller than a SOIC. Actually, it might be a USON, Microson, whatever the name is. But this is actually even smaller, right? So this one's actually I think a 4x4. So definitely better sized for a small module like this. Want to minimize footprint, but less sourceability, right? So if we're talking about something we can actually source and works out of the box, might be worthwhile to switch back. So I might still switch this back to the original. Again, I kind of over optimized for as small as possible at first because I didn't know how much space there was, and in fact, at one point we had previously we had the SIM, the eSIM on board as well. That has since moved off here so that we can connect that up. We can actually look at that easily. This is so this connection here. Yeah, so this is the SIM connection. This one also works out well for the being on the right side of the module here. Yeah, that connection is super easy. And then one last one. 6. All right, those signals were ain't no thing. This one, I believe, is a fat trace to ground. Yeah, that's 3v3. That's the input to the schematic. Yeah, so this is the incoming. So this is the 0 ohm that goes to the 9151. So we could add another via or 2 here. Yeah, I didn't like that. Let's try this, and then we'll switch to a different net class. So via. There we go. That's what I want right there. No, okay. Yeah, these little jumpies like this are not super helpful. All right, that should work. Let's see what that looks like on the 3D model. Yeah, so there we go. Okay, moving on. Let's do this one. Three. Okay, now we're starting to get into some difficult placements. More difficult placements. So we could do this here if we go to layer 3. See how that kind of goes horizontal. Well, we could fix that if we actually go. Oh, that was not what I wanted to do. So now we go here. This one's a layer 6 now, vertical to here. That preserves it. So now we should be able to get through there pretty easily. This one should be able to go horizontal. Here we go. Three. I was wondering why these traces look fatter. Let's go back to the net class with this one. I think we can change. Assign net class. I think we can change it to default. Let's see if that does it. No. These are all the predefined widths. The easy way to do this is just go and delete it. I'm trying to see if there's a way that I can show. I know there's an edit menu here, edit track and via properties. Filter by net. And then we can do it to net class. I think that should do it. It should get smaller. Yeah, there it goes. So that got smaller, back to the size I expected. Same thing here now. So we can go here, edit, track, DG14, and then set it to net class. That should make it smaller again. Yep, so there we go. Via 6. There we go. This one is going to ground. All right. This one's nice and easy here. Let's do this up to layer 6. So now this is a weird, slightly weird kind of idiosyncrasy that we're doing on this module generally, which is we're exposing the same SPI bus for the memory as for the external module. And now this is something that we did on the Elixir out of necessity. We basically ran out of what do they call it? Modules inside the NRF9160 part. So you can only really have, so you can have a combination of I2C, SPI, UART, but you can only have 4 total. And we ran out because when we were doing the Elixir, we wanted to have a UART that went to the click headers, and we wanted a SPI bus that went to the click headers, and we wanted an I2C that controlled everything on the bus. And we needed a UART to talk to the USB to serial. And so that's it right there. And so our option was to, and I think there's another one missing there. I think there's actually still, if you want to use you can only use, so we still have the pins hooked up for like because the UART going to the ESP32C3. If you have 2 UARTs, 3 UARTs, I guess in that case, you need to turn something off at that point. And so it really becomes this kind of like horse trading sort of thing there, where you only get 4, which is fine. I mean, we were trying to do a lot there, but ultimately one of the compromises we had was, well, we have this onboard SPI flash. We need to be able to talk to it, but also still use that same SPI bus with a different chip select to talk external to other stuff. So say we had a ADC that was SPI based. Well, that's fine, but it's going to be time sliced with the SPI flash, which isn't always the best option. All right, what is this thing doing here? I think we want to move this one down here. Yes, let's do that. Layer 1. So this signal is the reset line going to the ESP32C3. So we're using the backside here. And then we'll go here, layer 3. This is power. This is power. This is power. Well, I'm not going to hook that one up yet because I'm not sure what I want to do with that. All right, we're getting there, folks. What is left here? So this one is, so now this one, this is running backside. You see it's starting to get pretty crowded around the edge of the 9151 here. But this one is pretty important. This is the RX line going from the NRF9160 to the ESP32C3. Okay. Just redrawing my layers there. So it's not too bad. Oh, that's right, on top of the D plus D minus. I gotta be careful about that. So I'm gonna take that to layer 3. If you hear me beeping like that, that's actually me hitting the B key instead of the V key. There we go. You see we have some extra pads here. I'm leaving those till the end as well. Those actually will be topside pads, I believe. Not 100% sure yet. All right, this one's going here. This is the power going to the ESP32C3. These are these are pull-ups for that. How are we doing up here? All right, so we still have a couple of traces. That one's a straight shot down. How does that look? All right, so I think I want to get this one out to the right because there's a lot more room on the right side to go north-south. Route that straight in, thanks to the castellated edge. All right, how's this one looking? Pretty good. That one's going to be tricky. So this is the, looks like that. Oh, this is, okay, that's a low speed signal. That's good. So this is the rate protect for the flash. We can route this down here. Looks like I might have to bump that out of the way. No problem. If you're looking at me and thinking, wow, he's good at layout, the answer is no. I think it's really the 6-layer board. I'm not good at layout. Very grateful for that 6-layer board. All right, so this is the flash hold signal. This one, again, it's important to note when you have low speed signals, because something like this, we could take this much more kind of circuitous over here. So we're gonna take this, oh, what happened there? All right, you can see the implications of going diagonal. Oops. Aha, this is the analog. All right, let's do this. Let's go up here. Now we can go 3. A lot of room on layer 3 there. Layer 6. All right. We're at DG19. This one's going all the way over here. Wrong button. All right, we can snake this between these two, it seems. Bump some of that stuff. When I want to lock in a particular angle of the trace, I can just click. You can see that kind of gives me a new pivot point there. Then layer 3. Let's go on layer 6. Now this is a higher speed signal, so it's starting to get a little crowded in here. Also, things to be thinking about when you start getting your signals kind of squished in like this is as your signals get closer together, you get more crosstalk. So especially on things that are higher speeds, like a meso signal is basically the control signal, one of the serials in, serial out signals. And so the closer it is, 4 to 10 megahertz signal, you might have more crosstalk. So the more space you can get, the better off you'll be. I feel very confident having the low speed signals kind of right next to each other. A little bit less confident with the these higher speed signals. So for example, the ESP32C3 RX line being right there, not my favorite. But maybe we can bump it around. What can we do here? Actually, let's try this. Let's try and go. Don't want to do VN pad like that is showing. I was able to drop a via before, not on the pad. Okay, let's actually try and go on layer 3 here. Break some rules a little bit, go some diagonal. And then maybe go up the side here. Looks like we have some lanes open to us on the far side here. Ooh, I lied. It's power. Let's take a look at that again. We can highlight a net. How do we do that? Net inspection tool, highlight net. There we go. All right, so this is the kind of the top and bottom here. It's going kind of out to the right, going out to the pin edge, and then coming back in. This one is the MOSI signal. This is also going to be high speed. So we need to keep that in mind too. Move this guy over. This one is not hooked up for some reason. Let's hook that up. All right, so now we have MOSI here. That's an easy connection. But then how do we get to this one? Definitely need to go north-south. I would like to keep it somewhat separated from the MISO signal, if I could. But there's not a lot of spacing here. Well, one option we do have is on the top side. That's not bad. I don't think we can sneak it through here, unfortunately. Nope. That's not bad. Again, you break the rules towards the end as you get tighter in here. All right, so we're looking pretty good here. I know we're at an hour and 20 minutes. What is left? All right, so we definitely have some traces to get to the these guys here. All right, so I'm gonna refactor these a little bit. Oops. When I did this the first time, I basically just made a big grid. Because then we can have, one thing that's nice about that idea is you can then have the pads be on a grid, and it's a little bit easier if you're gonna make stuff, make a fixture or something later. These don't actually look like they're on a grid very well right now. Switch to a 1mm grid. All right, so that's the boot pin. I'm going to look down here and see if I'm actually on on whole millimeters. Sometimes when you start a footprint like off, it'll let you place it on like a 0.5 millimeter if it starts off that grid. Okay. That's not bad. Looks like this actually is connected. What's that connected to? Ah, that's an extra. Let's try switching this to the back side. This one might be tight to get to. Yeah, see, I must have, this one's allowing me to go 0.25. You look at the X down here. Well, it's allowing me to put it on 0.25 for some reason. I'm not sure why. Right, so aside from routing that poorly, I think this works. I am still on a 0.1 or a 1 millimeter grid, so I need to switch that back now. 0.1 is my standard. There we go. That's troublesome. Is this gonna work? 5, 6. Actually, at that point, you might as well. No, we need the space over here, fortunately. All right, this one just drops straight up via. This one disconnects here. That's nice. And we're missing one. That's this guy. Let's go back to the bigger grid. I think if I move these traces out, I think I should be able to get this on the same grid. Then I can switch back to the 0.1 inch grid, 0.1 millimeter grid rather. All right. Just realized a big downfall to this style of thing where you have multiple designs is normally I use this number right here, 450 unrouted signals, because there are a lot of unrouted signals here. All right, let's take a look at the layers though. So we will look at, all right, so we turn them all off, I guess. Just looking at courtyards right now. And what else? Drills, maybe? I don't know. All right, so let's just look at backside copper. So that's what this one looks like. So we see our controlled impedance pathway, which still is a TBD. I'm going to leave that for next time when we're going to do some cleanup. We're going to do some DRC, things like that. Looks okay-ish. Really, you know, what I'm looking for when I look at this sort of thing is like, is it north-south? Generally, yes. So that is about what I expected here. Let's look at layer 5. This is the power. I expect it to be it's basically just the cutouts of the vias. Now, if we were doing blind and buried vias, we could actually not have cutouts in this plane, right? So if you have blind and buried, you get to like have more contiguous planes. We do have blind and buried, so Swiss cheese it is. This is the inner two. Sorry, that was the one we were just looking at. Sorry, that was the ground plane. Oof, man, not getting that right. Okay, so this is the ground plane. This is specifically for the controlled impedance coming off of this one, off of the USB. If we needed to do, top and bottom RF, we could also do that. This one is the power plane, and so we see here these two. These are connected here, and then again a little bit Swiss cheesy, but ultimately quite a bit of copper here. And we can do some stitching later if we need to. That's via stitching. This is our inner layer 3, which is inner copper 1. This is our signal layer that's really meant to be mostly east-west, but as you can see, some of it is diagonal. Then we have our topside copper layer. The most important thing being for RF signals that we have a very clean signal here. Kind of see our via stitching around the RF traces. I didn't do that down here, which is interesting. I thought I did, but we'll take a look at that next. And then finally, this is the top side layer. So this is the component layer. Remember, we can only put components on our top because, well, it's a module, so we're gonna solder it down. So in terms of rat's nest that I see still unconnected, this one is definitely here. I already know what that is. That's because we never hooked it up to anything. So we should do this, and we can do this, hook up to ground. Hit F8. So now that should be connected to ground. There we go. And then this one is not hooked up to anything. Let's see that X signifies. We could start to do things. So now if I turn all the layers back on, we can start to do things like this. If we wanted to have a ground pour in here, very easy to do that sort of thing. You basically just select the net you want. In this case, it's just because it's looking at what inner copper layer, what inner pores you have available and saying, hey, do you want it to be top side, bottom side? What do you want this thing to be? And then like I talked about here, you might want to do something like this too, where we, that one violated DRC. All of these are violating DRC. It does not like what I'm trying to do here. There we go, finally placed one. So we might want to, definitely want some kind of stitching around here. I'm not sure what. Another easy way to do this is you can just copy paste, but now it will not check DRC as you do that live. So that's another thing to do during some checks there. Looks like these are, oh, well, look at that. Nothing like a good catch there. We didn't hook up power. And yeah, so that is another thing here. You see that it's got some internal multiple pins here, which is nice for that catch. But that is definitely another thing I have to do in the checking realm. We got to put some VDD3P3. I assume that's 3P3 is 3V3, or it's just the third rail. And then this is the analog here. So definitely need to add some decoupling. I will go read the data sheet off camera, and I will do that for the next time. Good catch though, Chris. Yeah, and so when we do the error checking next time, we'll also do ERC and make sure we didn't miss anything here. Things like this where, the mag PIO, which is like one of the magnetics things, I think that controls the antenna. It potentially can control a cellular antenna. We're not using any of that sort of thing, so I'm going to just do this sort of thing. And when we do checking, then it'll say, hey, you didn't hook up DEC0, you didn't hook up aux. So like I said, I have access to the DK. I'll go and double check on there. What this will ultimately probably do is add a couple more components in here. Have a couple more shuffles that'll need to happen as a result because, well, I probably should have done that prior. But in terms of like spacing and availability, I feel pretty good about what's available here. Okay, let's take one more look at the module itself. Now drawn with with some signals on it. So that feels pretty good. We're getting there. And in the next stream, hopefully we'll have error checking and manufacturing of the Dram 1, and then we can move on to, I have many other things that I would like to do in the hardware stream. If you have any thoughts, you can always tell us over on our forum. We have lots of conversation over there. But let me know if you want to see anything particular with this design or other designs around the Elixir or Stentus, which is our display. And yeah, thanks for watching. We'll see you at the next one. And